Hi, welcome to Autodesk Simulation TV. Today we're going to discuss random vibration, what happens to my part under random vibrations. My name is Tessaro and I will be guiding you through this process. Our problem here is we're going to be looking at this. This is actually a spring that sits under a tractor seat attached to a tractor. The kind of tractor you'd see plowing the fields or taking the corn down at the end of the year. And what we're going to learn is what kind of stresses would this model experience under random vibrations. Random vibrations are different than any other type of load in that the vibration does not follow a periodic pattern, but statistically we could look at information that we gather using an accelerometer would be an example over a period of time, and we would find that if we took different time samples that the decomposition of this acceleration data would be similar between one sample and the next. So using this information we'll be able to see how this model will produce stresses and therefore guide us in how we can further improve the design. This will involve a two-step process, and while I talk about this, we could see a nice colorful picture of the kinds of results we might see from this type of analysis. The two-step process is going to involve performing a modal analysis and also performing a follow-up random vibration analysis. We're going to walk through both of these, including importing the model and going through some short model preparation as well. To perform the modal analysis, we're going to import the geometry, mesh the model, define material, apply boundary conditions, and then we're going to perform the modal analysis. We're going to review the log files to learn what the modal effective mass may be, so that we could obtain a minimum of 80%. This will be useful when performing our restart analysis, in this case the random vibration analysis. If we didn't see 80% modal effective mass obtained within the number of frequencies we analyzed, we would reanalyze the model to include more frequencies. The next step would be to perform the random vibration analysis. The random vibration analysis is assumed to be enacted through the model through its boundary conditions. So our main purpose will be to supply our power spectral density, or acceleration spectral density would be another term that we could use for that. After that we'll be able to perform the analysis, review the results, and decide whether we need to make a design change. Let's begin with our analysis. The first step will be to bring in the model. I've created a simple geometry in a different CAD package, and I'm just going to go through the steps of opening that file. In this case I'm going to be using an intermediate file format such as a step file, but we can open several different file types. We'll be asked the question of what type of analysis would we like to perform, and under the linear branch we'll choose the option to perform the natural frequency modal analysis. Choose OK. Our geometry will appear in the interface on the right hand pane, and on the left hand side we have the model tree or the model browser, and anything that needs to be defined before we can perform the analysis is highlighted in red. So I'm going to access the meshing tab and I'm going to generate a mesh on this model. Because this part represents a small portion of a larger assembly, I'm going to add some additional elements that will help represent what's not in this geometry right now. So if this is a spring that attaches to the tractor on the bottom, and on the top a seat is on there, and on top of the seat is a human, that human might weigh a couple hundred pounds. So we would want to represent that mass both in our modal analysis so that it could be considered also in our random vibration analysis. So let's look at the steps to do that. I'm going to select the surface on the top of the model here. And I'm going to go to the Draw ribbon and then use the centroid creator, which will allow me to connect centroid to surface with spokes. I'm going to choose OK, and that creates a series of lines on the top of the model that connects every node to a central location. On that location is where I'm going to put my mass. So I'm going to toggle the display of my construction vertices and then select my vertex right in the middle there. And I'm going to be able to right click and choose to add a nodal force. Actually not a nodal force, but a nodal weight is what I'm interested in. I'm going to put my number in. I assume about 200 pounds is what I'm going to consider. I'll choose OK. Now in the model tree I need to define some information before I can proceed. Anything that's red will need to be defined. I'll define my material for my spring first. I'll say maybe this is a spring steel, and I'll go as far as saying it's a 4130. For these elements that I created in the model, I'm going to use a beam element to connect this mass to the rest of the geometry. And to size this beam element, I'm just going to use a technique where I want it to be similar in size to the adjacent mesh. So I select a line in the model that represents an average mesh line, and then I could right click and inquire on its length. It gives me a number about 0.3. That's the number I'm going to use. I just want to develop the stiffness for these elements to be somewhat proportional to the rest of the model. I'm going to right click on the element type and define this as beam, and then I could right click on the element definition, and within the element definition I could choose to edit the cross-sectional libraries. I'll need to select this row first before this button becomes enabled. I'm going to say that I'm dealing with a round cross-section and enter my inquired line length number of 0.3. I'll choose OK and then OK again. I'm going to use a material that's similar in nature to what I've defined for the rest of the model so that I get a stiffness that's appropriate, but I'm going to make an alteration such that the mass density is significantly less. I don't want to introduce mass to the model through these intermediate elements. I just want to provide a connection between my added lump mass and the rest of the model. So I'm going to edit my material properties, and I'm just going to add about 8 zeros to make my mass density less significant. The last thing we need to do is to add some boundary conditions. So I'm going to select by surface, rotate my model, then right click and choose to add surface general constraint and make it fully fixed. At this point we're ready to perform the analysis, so I'll do so. Having run the analysis, I'm not especially interested in the graphical display of the model. I'm going to go to the Report tab, scroll down, and view the analysis log file. Within the log file, I'm interested in viewing 3 sets of information. One is the modal effective mass in each of the global directions, X, Y, and Z. And I want to see a number that's above or equal to 80. In this case, for the 5 frequencies that were solved by default, I see that 99% of the model's effective mass has been considered, both in the, I should say, in all 3 directions, X, Y, and Z. So I don't need to go back and reanalyze this. I'm ready now to go back to the FEA editor, and then I could right-click on the analysis type and choose to change the analysis type to random vibration. A prompt will appear asking if I'd like to make a copy of the design scenario. I'll choose yes. Within this new analysis type and within a new design scenario as indicated in the top, I'm going to right-click on the analysis parameters and choose to edit. I'll click on the analysis data button in the top right, and our goal here will be to indicate what kind of power spectral density or acceleration density that we're going to consider during the analysis. I can consider either acceleration squared per hertz versus frequency or g squared hertz per frequency. So I'm going to choose g squared hertz. We could define our damping ratio, and I'm going to leave it at an insignificant value so I can get the maximum response. And then I can either enter in my data points manually, or I could choose to import as a CSV file. In this case, I'll choose to import my CSV file and indicate the direction, which will be in the vertical direction. I'll choose OK, OK again, and then I'm ready to run the analysis. Having run the analysis, by default it's going to show me my displacement results. I can access the stress and see what the resultant stress is, and this indicates the resultant of 5. I had performed a modal analysis which provided 5 mode shapes, and this is the resultant of each of those mode shapes' participation in this final result. If I were interested in looking at each mode shape's participation, I can go to the Results Options ribbon and toggle the resultant checkbox. Thank you for watching this presentation.